All right, in this video, we're going to do an example of a chi-square test of independence, but it's not going to follow the procedure that I did in the previous video. This is more like a skill development video. We're going to do all the skills necessary to be able to do a chi-square test of independence. Okay, so let's look at this. This is right off of one of my lesson sheets for class. We have a sample of 71 adult males. That means that N is 71. That means the number that goes down here is ultimately going to be 71. Okay, 71 adult males indicates that 27 of them consume a high cholesterol diet. Okay, so here's high cholesterol diet, and also have been diagnosed with heart disease. Okay, so two categories. We have high cholesterol diet or low cholesterol diet. Okay, so those are our two categories on one variable. So this variable, this categorical variable, is type of diet. And then the other categorical variable is whether you have been diagnosed, the person has been diagnosed with heart disease. And so there are two categories. They've either been diagnosed with heart disease or they have not been diagnosed with heart disease. 27 of them have a high cholesterol diet and also have been diagnosed with heart disease. So here's our 27 right here. The rest of the sample is summarized in the contingency table below. And so 11 people have no heart disease, but they do have a high cholesterol diet. 15 people do have heart disease, but they actually have a low cholesterol diet. And then 18 people have no heart disease and a low cholesterol diet. Okay, and so what part A says here is complete the sample values contingency table. So here we go, sample values. Sample values is the same thing as observed values contingency table. Okay, then it says, and then complete the expected values contingency table. That's right over here. And we learned how to do that with our formula, expected value of a cell, okay, is equal to the row, or you can do it either way, row total or sum times the column, whoops, let's fix that, times the column sum or column total, it's the same thing, divided by the sample size, which is N, okay? And so what we're going to do is the first thing we need are our totals, our column totals. So this will be the total for this column. This will be the total for this column. So 27 plus 15 is 42, and 11 plus 18 is 29. Now we need our row totals. So we add up the row and put the total here. 27 plus 11 is 38, put that here, and then 15 plus 18, that's 33. And 38 plus 33, that's 71. And 42 plus 29, that's also 71. So we have our sample size, we have our row totals, and we have our column totals, or we can call them our row sums and our column sums, okay? So what we're going to do is we're going to transfer all of these numbers over to the expected values table. So we'll put a 42 here, and then we'll put a 29 here, and we'll put a 71 here, and then we'll put a 38 here and a 33 here, okay? And now to get this expected value for this cell, we're going to multiply 42 times 38 and then divide it by 71. Okay, so that'll be 42 times 38 divided by 71. So let's go over to a calculator. 42 times 38 divided by 71. 42 times 38 divided by 71. Looks like it gives us 22.479. This 8, this fourth 8 is going to make this third 8 into a 9. So 22.479. 22.479. Okay, great. Now to get this number, we can get it in two ways. We can either do the column total, 42, times the row total, 33, divided by 71. The other way we could do it is we could simply subtract 22.479 from 42, but I want to do it the calculation way. So we're going to do 42 times 33, 42 times 33 divided by the sample size, which is 71. So 42 times 33 divided by 71, and that's going to give us 19.521. We're going to stop after 3, 521. So 19.521, 19.521. And if you were to add 19.521 plus 22.479, you would get 42. Okay? And now to get these expected values, we can either do, subtract the row sum minus what we already know, but I want to do the calculation. So we're going to do 29 times 38. I'll do that over here. 29 times 38 divided by our sample size, which is 71. So 29 times 38 divided by, oops, yeah, that's right, divided by 71, and that gives us 15.521. So 15.521. And now to get this one right here, we're going to do 29 times 33. 29 times 33 divided by 71. 29 times 33 divided by 71. And that gives us 13.479. This 8 will become a 9 because of this 8. 13.479. 13.479. And that's it. We did it. We completed the sample values contingency table by adding up the rows and the columns and getting the total, or the sample size. And then we completed the expected values contingency table. Now we're going to use this information and we're going to answer a couple more questions. All right, so part B to this question is asking something interesting. It says, if the two variables are independent, so let's assume that they're independent, then what is the probability of having both heart disease and a high cholesterol diet? Okay, so here's what that means. What this is basically asking is this, if the two variables are independent, then the average or most likely or expected response would come from this table. So if the two variables actually are independent, then the expected values table is what we would expect. So how many of them would we expect to have heart disease and high cholesterol diet? Well, here's heart disease, here's high cholesterol diet. We would expect 22.479 of them. 22.479 of them we would expect if the two variables were independent. Now here's what's funny. That's actually the question being asked down here in part C. It says if the two variables are independent, then how many people out of the 71 would we expect to have heart disease and high cholesterol diet? Well, that's 22.479 right out of the table. So this is actually the answer to part C. But part B says, what is the probability of having both heart disease and high cholesterol diet? Well, that's going to be our expected value divided by our sample size. So the probability of heart disease, let's write it like this. The probability of heart disease and high cholesterol is going to be equal to our expected value, 22.479, divided by our sample size, 71. Let's go to the calculator. 22.479 divided by 71. And so it's going to be 0.3166. Let's say 0.317. Okay. Actually, we'll stick with 3166. So it would be 0.3166. Okay. So if you want a probability that of two categories crossing over when you assume they're independent, then you just take the expected value and divide it by the n. And then if you want to know how many out of the 71 or how many out of the sample size, the answer is exactly the expected value that's in the cell. All right, let's just look at one more part to this question. All right, now let's look at part D of this question. It says, the first thing says, what is the degrees of freedom? Okay, well, let me remind you that the degrees of freedom are going to be equal to the number of rows. So how many rows are there? Here's one row, here's another row. Okay, so there's one row, two rows, minus 1. So 2 minus 1 times the number of columns. How many columns are there? 1, 2 columns, minus 1. We're going to multiply them. So 2 minus 1, that's 1. Times 2 minus 1, that's also 1. And what is 1 times 1? Well, that's 1. And so the degrees of freedom for this particular chi-square test, degrees of freedom is 1. All right, so I'm going to write that over here. df equals 1. And now we'll move on to the next part of the question. All right, so the next part says, what is the chi-square critical value for this test at an alpha of 0.05? So if alpha is 0.05 and degrees of freedom is 1, then what is the chi-squared critical value? Well, to do that, we're going to have to go over to the NumWorks calculator or a paper table or Minitab. We're going to use the NumWorks calculator. We got to go to distributions. We're going to hit OK. We're going to go down to chi-squared, hit OK. Degrees of freedom is 1. We just calculated it. OK. Then hit next. Now remember, we don't want the left side shaded. We don't want the left shade. We don't want a middle shade. We want the right tail shaded. So we want this one down here. Hit OK. Whoops, I didn't change it. Let's go down this one. Here we go. And then hit OK. All right, so right tail shaded. Then go over here, and in the p-value, this is the box for the p-value. That's where we put the alphas. And we put in 0.05. And our critical value for chi-squared is 3.841459. Okay? All right, let's see here. So we'll write it over here. We'll say chi-squared critical is 3.841459. 841459. Barely squeeze it in there. Okay? All right, what about the next part? It says, well, what is the chi-squared test statistic for testing the significance of independence between these variables? Blah, 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 blah. It's just saying, what is the chi-squared test statistic given these expected values and these observed values? Okay, well, this is going to take a good bit of math because I want to remind you that to get the chi-squared test statistic, we have to add up, we have to sum up a bunch of things. What are we summing up? Well, let me remind you, we're summing up. We have to do the observed value minus the expected value, then square that number, then divide by the expected value. Okay, this will give us one number, and we have to do that for 27 and 22.479. That's one number. Then we have to add that. We got to do it again for 15 and 19,521. Then we have to do it again for 11 and 15,521. And then we have to do it a fourth time. We got to do it for 18 and 13,479. Okay, so I'm going to go ahead and write out this addition problem, and I'm probably going to speed it up just a little bit. Okay, so now we've got our summation. We're summing up 4 things for our chi-square test statistic. Now we're going to have to plug this whole thing into a calculator. So I'm probably going to speed that up too while you watch me enter this whole thing into a calculator. All right, so we just entered the entire summation calculation into the calculator. Now we just hit OK or enter or execute, and here is our chi-square test statistic, 4.789598. Okay, so our chi-squared test statistic, I'll write it up here. Chi-squared is equal to 4.789, 598. Okay? All right, that's, and then we have one thing left. It says, what is the p-value of the test statistic? And to get the p-value of the test statistic, we're going to go into the distribution, the same place where we went to get the critical value. We're going to plug in 4.789598. Okay, so we're going to go here. We're going to go down to distributions. Okay. It looks like, I think we're still, yeah, we still have degrees of freedom. It's still chi-squared. Degrees of freedom is 1. And then we're going to hit next. And now we're going to, remember, we're going to change it to the right tail shading. Hit OK. And now, instead of putting in a number over here in the p-value, we're actually going to put in our chi-square test statistic right here, which is 4.789, 598. And then we'll hit execute, and this is our p-value. It's 0.028632. So our p-value is 0.028, 632. And that's it. That's all they asked us to do. Now, I do want to point out that our p-value here is less than 0.05. And that means that we would reject the null hypothesis if we had gone through the whole procedure here, okay? Also, our chi-square test statistic is 4.79, and our critical value for the chi-squared is 3.84. And since our chi-squared statistic is larger than our critical chi-squared, we would reject the null hypothesis, okay? All right, so I hope this video helped you with some of the skills. We're going to do one more video with a full-fledged example of a chi-square hypothesis test.